So in this lecture, we're going to look at some examples of how we can find integrals of rational functions using this idea of a partial fractions decomposition. And just kind of being honest about it, the partial fractions part is really the most interesting part of the whole thing. Once we get that done, once we get these rational functions split up into smaller rational functions, the integrals are usually pretty straightforward. Right, so I need to start by rewriting this expression here. And if we factor this, this becomes 1 over x plus 3 times x plus 1. So this is going to split up to a over x plus 3 plus b over x plus 1. Right, then I'm going to get rid of all the denominators. I'm going to multiply this through by x plus 3, x plus 1. So everything cancels on the left side, so this will be 1 equals a times x plus 1 plus b times x plus 3. Right, and if we multiply out the right-hand side, this is ax plus, I'm going to rearrange the terms here as I do this, ax plus bx plus a plus 3b, and this has to equal 1. All right, so if you think of that left side as being 0x plus 1, then we can factor this, right? I'm going to make this x times a plus b plus a plus 3b. So then a plus b has to equal 0, and a plus 3b has to equal 1. All right, well, this first equation, this tells me that a is equal to negative b. So if I make that substitution here, this becomes negative b plus 3b equals 1. So that's 2b equals 1, or b equals 1/2. And again, substituting back into here, that means a is negative 1/2. Okay, so now we're ready to talk about the integral part. So then the integral of dx over x squared plus 4x plus 3 is equal to the integral of, and let's make sure I get these in the right order, negative 1/2 over x plus 3, right? The negative 1/2 goes with the x plus 3, good, dx, plus the integral of 1/2 over x plus 1 dx. All right, if we go ahead and pull these 1/2s out, this is negative 1/2 integral dx over x plus 3 plus 1/2 integral dx over x plus 1. And like I said at the beginning, these integrals aren't particularly complicated. This is negative 1/2 times the log of the absolute value of x plus 3 plus 1/2 times the log of the absolute value of x plus 1 plus a constant, and that's it. Right? That's where I'll go ahead and stop. That's my final result. All right, so let's take a look at this one. This one is a little more interesting, but again, what makes this interesting is just the partial fractions part, not so much the integration part, right? So if I take a look at this this expression and factor the denominator, this is x plus 1 over x plus 2 squared. So remember how we do this, and this is going to equal a over x plus 2 plus b over x plus 2 squared. Now we'll clear those denominators, multiply both sides by x plus 2 squared. The left side is x plus 1, and the middle part here, this is a times x plus 2 plus b. All right, then we multiply this out. This is x plus 1 equals ax plus 2a plus b. And good, it goes pretty quickly from here, right? We compare the x terms. So a has to equal 1. And then we compare the constant terms. 2a plus b equals 1. And if we put 1 in here for a, 2 plus b equals 1, so b is negative 1. Okay, excellent. Now I can do the integral. The integral of x plus 1 over x squared plus 4x plus 4 dx is equal to the integral of dx over x plus 2, that's putting the a into here, minus the integral of dx over x plus 2 squared. Or well, this first integral, again, the integrals now aren't super interesting. This is just the log of the absolute value of x plus 2 minus, and let's think of this as the integral of x plus 2 to the negative first, excuse me, to the negative second dx. So this is the log absolute value x plus 2 plus x plus 2 to the negative first plus a constant. And since I did this integral, I really should have put the constant up here on this step as well, because we already did part got rid of part of the integral part. And this is it, right? I would rewrite this the log absolute value x plus 2 plus 1 over x plus 2 plus c. But really either of those are would be perfectly good ways to write the result. Okay, so there's two kind of basic examples of how we can use this partial fractions method. In the next lecture, we're going to look at some more examples that are a little more complicated or have things going on that are a little more interesting.